This example is actually very easy. The sum n equals 1 to infinity of 2 to the n is 2 plus 4 plus 8 plus 16. So it's adding on larger and larger amounts every time. And even the terms of this series are going to infinity. The whole series itself is definitely going to infinity. In fact, here's a quick theorem. Whenever the limit as n goes to infinity of the sequence, which we've been finding earlier, does not equal 0, then the summation, the series, is going to diverge. It's going to head towards infinity. The opposite of, or the converse of that isn't true. Lots of times you can have a limit that goes to 0, but the summation still diverges. But to see why it's true that if the limit doesn't equal 0, then the sum does diverge, just think about a limit that goes to something like 5. Then as you're adding all the terms, then eventually you're just adding plus 5 over and over and over again. And 5 added over and over and over again gets to infinity. So if you don't end up adding smaller and smaller bits, you definitely blow up and add to infinity. We should see one example, though, of a series that equals infinity, but for which the terms do head to 0. This is the classic example. It's the summation n equals 1 to infinity of 1 over n. So if you fill in the n value, the values of n there, you get 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... It does go on forever. And I'm going to say that this turns out to equal infinity. But first notice that it does get smaller and smaller. Each fraction that you add on is a little bit smaller, and they do get closer and closer to being 0. But look what happens if I try to draw a picture of it. I just picked a random shape, a circle, but it would work the same if you draw the picture with a square. So first I fill in a half there on the left, and then a third, and a third is more than a fourth, so that's what it looks like. About a third of the circle is filled in next. But then the next thing that I want to fill in is a fourth, and the problem is there's not room. If I want to fill in a fourth, I could fill in the rest, but then I'll still have that little wedge-shaped piece where the fourth and the third overlap that I need to add on. And it doesn't matter what shape you start with, you're always going to run out of space to fill it in. And so that's a very rough argument that when you add up a half plus a third plus a fourth plus a fifth, it never stays inside of any shape that you can draw, so it heads to infinity. However, there's a nice proof of this using integrals, and that's going to be for the next section, 11.3. We'll call it the integral test, which will allow us to prove that this example and other examples add up to infinity.